All right, today we're going to be working on pages 10 and 11 in the study questions packet. These two pages and page 12 will be completed in class. I'm going to go through this first example with you fully, and then I'm going to go through the next example about halfway and have you finish it up so that you can see what you do in another situation, and then you'll finish up the last page on your own. To begin, what we're going to look at here is carbon-14 and nitrogen-14. And carbon-14 is a radioactive isotope of carbon, and it will decay over time. And it takes about 5,700 years to go from 100% of whatever is radioactive to half of that material that's radioactive within the rock. Just to emphasize this point, when we're looking at the radioactive material in a rock, we are not looking at the entire rock. The entire rock is not radioactive. We're looking at just those radioisotopes that are, in a sense, sprinkled through the rock randomly that are decaying over time. So if we had a sample that had this sort of idealized 100 grams, and I'm doing this for mathematical purposes, and we were to take that and go 5,700 years into the future, 50% of that 100 grams would decay to a stable end product, but 50% would still be radioactive. So I've illustrated that here in the table. Here's the original amount, 100 grams, and this 100 grams is all the radioactive carbon-14. And at the start, 0 grams is radioactive. But after one half-life, half of this original amount has decayed down here to a stable end product. But 50 grams, or half of the sample, is still radioactive. So from a mathematical standpoint, being able to calculate the amounts of radioactive to stable end product is simply a matter of simple math. What we're going to do for each half-life is take this number that we begin with. In this case, after one half-life, we'll have 50 grams of radioactive material. We'll take this amount and we'll cut it in half. So 50 grams divided by 2 will give us 25 grams. 25 grams divided by 2 will give us 12.5 grams. 12.5 grams divided by 2 gives us 6.25 grams. And then 6.25 grams divided by 2 is 3.125 grams. So what's happening over time is after each half-life, in this case 5,700 years each time, half of the sample decays to this new amount of radioactive material. But the other half of the 25, I should say of the 50 grams, becomes stable. So to illustrate that, probably the simplest way to do the math is to throw 100 grams up in the top row here, and then subtract the radioactive amount from that 100 grams, which is the original starting amount. And we see that 100 grams minus 100 grams gives us 0 grams. And this is done because the mass of the rock does not change. I should say the mass of the radioactive isotopes does not change in the rock. And so what happens is, mathematically, if we just put the 100 grams up top and subtract the radioactive amount, we'll always get the complement to equal 100 grams. So 100 minus 50 gives us 50 grams. And if we do this for the one that we just found, 100 grams minus 25 grams gives us 75 grams. 100 grams minus 12.5 grams gives us 87.5 grams. 100 grams minus 6.25 grams gives us 93.75 grams. And 100 grams minus 3.125 grams gives us 96.875 grams. So mathematically, we can see how this table can be filled out, but let's take a look at what these numbers sort of represent. What we're seeing is the mass of the radioactive material declining by half from the previous amount each half-life. But then that same amount is added to the existing stable end product each time. And the easiest way to represent this mathematically is to always subtract the radioactive amount after each half-life from the original amount, in this case 100 grams. So the time elapsed portion is very simple. We're not just going to double this number each time. We're going to add 5,700 years. So the first one will be doubled. And we'll see that by simply adding 5,700 years. And so we end up with a new number, which is 11,400 years, or 5,700 years plus 5,700 years. If we go ahead and add 5,700 years again, then we'll end up with a new number, 17,100 years. 5,700 years added to 17,100 gives us 22,800 years. And lastly, 5,700 years plus 22,800 years gives us 28,500 years. So each one of these increases in time is equal to the last. We're simply adding 5,700 years. From a percentage standpoint, I chose 100 grams so that we could see how the numbers will match for the percents. The percents, however, are going to always be the same for every substance, because the idea is, of course, that you're going to take 50% of the amount that you have that's radioactive after any half-life. And so the numbers here for the carbon-14 and nitrogen-14 are going to be exactly the same numbers as the amounts or masses that we have up here. And so 100% divided by 2 is 50%. That gives us and then 50% divided by 2 gives us 25%. Now to find the complement of that, in this case, we can simply look up here and realize that that's a 75 to 25% ratio. And then we take half of 25% and we get 87.5%, 6.25%, and 93.75%. And lastly, 3.125% and 96.875%. Now again, these numbers are the same in this example. But if I started with a larger amount up here, let's say 200 grams, like we're going to see in the next example, these numbers will always remain the same down here. They'll always be 100%, 50%, 25%. But up here, 200 grams would be halved, and then we would have 100 grams, and so on. So the amounts can vary. Sort of like the numbers on a test or on a quiz can be, any number of questions. But getting them all right is going to be 100%. Getting half of them right is going to be 50%. And so this percentage is an important concept to remember, because the whole idea of half-life is dealing with 50% of the amount of the sample that's radioactive at any given time. All right, so what we'd like to do next is to graph this data to see how these amounts change over time. We can see that they decrease, and we can see that they increase. But there are a few things that we might be able to pick up from representing these on a graph that aren't necessarily easily seen here or as obvious. So to plot these, it's very simple. You're going to plot on the x-axis the half-life time, so 0, 1, 2, 3, 4, 5 half-lives. And for carbon-14, we'll be plotting these numbers with respect to that time. And for nitrogen-14, we'll be plotting these stable numbers with respect to each half-life. So to begin, we'll go to 0. And our first amount for carbon-14 is 100 grams. So we'll go to 0, and we'll go all the way up to 100. And we'll put a little dot. Now, you don't have to do these in color. You can colorize these if you want to afterward, but let's do it in pencil first. And so the next one's going to be 50 grams after 1 half-life. So go to 1 half-life, go up and find 50, and make a little circle. After 2 half-lives, it's 25 grams. So right between the 20 and the 30, make a little dot. After 3 half-lives, we're going to be at 12.5 grams, which is just above the 10. After 4 half-lives, 6.25, which is just below the 10. And then the last point is 3.125, which is just above the 0 line. So what we have here are the decreasing amounts of carbon-14 over time. In this case, 28,500 years, or 5 half-lives. Now, to actually illustrate this a little bit better, you might want to create a line, and you should, from each point to show how this change over time is a line. And we'll go ahead and plot the nitrogen 14 using a box symbol. And that's because, so the first one is 0, 0. So we started at 0 amounts at time 0. And we're using a box because the box can go over the circle here at this 50%. Because, of course, these are when the first half-lives when you have equal amounts of both radioactive, isotope, and stable end product. Then after 2 half-lives, we're going to go up to 75 grams, and then 3 half-lives is 87.5 grams, just below the 90, and then 4 half-lives is 93.75, so just above the 90, and lastly, just below the 100 will be the 96.875 grams at 5 half-lives. And so we should connect a line to show how these increase over time. And then it's a really important final step is to actually shade in underneath each line. And so if we shade in lightly underneath this line, we'll see how the overall amount of radioactive carbon-14 decreases over time. And we can see, if we shade in under the blue line, how the amount of nitrogen-14 increases in complement to that radioactive amount decaying. All right, so we're going to move on to page 11. And on page 11, we're starting, as I mentioned earlier, with 200 grams. But notice that the percentages are the same as the previous example. So we start with 100% of the original amount, in this case 200 grams, and then we cut that in half, or 50% of that amount, which is 100 grams. And then 25% of that original amount is half of the second amount, so that's 50 grams. So to figure this one out, we simply take the 50 and we cut it in half, and we get 25 grams. 25 grams in half is 12.5 grams, and then 6.25 after 5 half-lives. So because we started with a larger amount of radioactive material in a rock, we end up after 5 half-lives with more of that sample. So if we take a look at the math between the radioactive and stable amounts, we see that at the first part we start at time 0 with 200 grams minus 200 grams giving us 0 grams. After the second, 200 grams minus 100 grams giving us 100 grams. So what we should probably do is just go right ahead and write these 200s right across the top and subtract them each time. And so when we get to the third half-life, we'll see 200 grams minus 25 grams gives us, in this case, 175 grams. So the stable end product, in this case B, increases by the amount that this decreases each time. So 175 grams plus, 200 grams minus 12.5 gives us 187.5 grams. And then the last one, 200 grams minus 6.25, gives us 193.75 grams. And just like in the last example, each sort of half-life time is simply added to the previous time. So you go from 0 to the first half-life, and that is the time unit that you're going to be adding each time. So in this case, 7,000 years. So 7,000 years plus 7,000 years is 14,000. And then we'll go ahead and add another 7,000 to get the amount of time after a third half-life, which is 21,000 years. And then you'll add 7,000 to the next one. So I'm going to ask you to, at this point, to finish up the half-lives here, the percentages, which should be always the same, which are always the same, and then go ahead and graph the mass amounts with circles and squares down here, just like we did in the previous example.